So, I will continue our calculation. So, what we have seen that this density of states, density of modes of vibration is this, okay, in the range of frequency nu to nu plus d nu. Remember that it is not, so it's this is not a volume of physical, this is not a physical volume. Okay. So, this volume occupy the number of modes which are having the frequency nu to nu plus d nu. Okay. So, what will be the total number of modes in that frequency range? So, that is this is the total number of modes in that frequency range. Okay. So, having frequency nu to nu plus d nu. Okay. So, here, so this the then we can tell that this is the frequency, this is the number of modes having frequency nu and the small frequency difference range d nu. So, if I multiply d nu, so I will get total number of modes. Okay. So, then this part we can tell this is the density of modes, means number of modes per unit frequency. So, this basically density of states is defined Z nu, it is basically defined d n, say d n this number of modes, okay, or one can give capital N or whatever, capital N whatever, okay, d n by d nu. Okay. So, that is the per unit frequency how many number of modes. Okay. So, do not be confused with the physical volume. Okay. So, then we will think why I have not divided by the volume of one mode. Okay. So, now so we got the density of modes at frequency nu. So, I do not need them, I need only so I got everything in terms of frequency. So, I got density Z nu, density of modes at frequency nu equal to 4 pi L cube, 4 pi L cube by V cube velocity. So, nu square. Okay. So, here you can see this density of modes varies as a function of square of the frequency, right. So, higher the frequency, so this density will varies as a square of that frequency, right. So, at higher frequency density will be very high, So, it is basically if you draw this, so Z nu it will vary like this parabolic curve nu square, so it will vary like this, right. So, it is the nu, Now, what we have to, so what we got, I have a solid crystal, right. It is treated as a continuum medium, okay, instead of discrete atoms arranged in this material. So, that was the assumption of this Debye, okay. And now there, so this system will vibrate, okay, as a whole, and we will get mode of vibration, different mode of vibration. So, each mode will have the frequency, different mode will have different frequency. So, first mode, second mode of vibration, third mode of vibration, nth mode of vibration. So, their frequency are higher and higher and higher. Okay. So, now what I want to do? So, this is my system, this system, solid system I have expressed in terms of mode of vibration. I know the density of modes as a function of nu frequency, right. So, I want to calculate the total energy of this system. So, each mode will have energy because it has frequency nu, each mode will have energy, different mode will have different energy. Now, each mode if its frequency is nu, so its energy will be h nu, right, its energy will be h nu. But this mode, this energy may be the lowest energy and it may be the down state of the at ground state it may happen. But when you will increase the temperature, then what will happen? So, this mode I have considered just one mode, I have many modes. So, one mode of frequency nu, it is at say down state having the energy h nu, because this nu is known to me. So, its energy is known to me h nu, but all the time it will not have this energy h nu, although its frequency is nu. So, it can at when it will be thermally excited, when this thermal energy will given to the system. So, these modes will be excited in higher energy. Okay. So, each mode have possibility to go at higher energy at excited energy levels, excited states having the higher energy level. So, it will occupy higher energy states having the same frequency. So, its energy will change. So, there are possibility of a particular mode to have different energy as a function of temperature, depending on temperature. So, what we have to do? We have to know the average energy. We have to know the average energy of each frequency for each mode. Okay. So, now what will be the energy distribution having the frequency nu, so but it can have many energy levels. So, initially say its ground state it is here, so its frequency its energy is h nu. Okay. So, what will be the higher energy states for that mode, excited state for that mode. So, that one has to know. Now, again in this case Debye assume that, consider that that solid is made of atoms, atoms are arranged in the system. Okay. As a whole it is vibrating, and giving different modes. So, if this solid our cube having length L of each side, if it contains total number of n atoms, total number of capital N atoms, okay, and then basically all atoms are vibrating together. Now, he considered that this total number of modes. So, as we have seen earlier that n number of atoms are there in case of Einstein. So, if it is oscillating like harmonic oscillator, then its frequency is same, frequency of all oscillator are same, but they have energy distribution n h nu. Okay. So, for each nu having the energy distribution following having the different energy states, So, 2 h nu, 3 h nu. So, this is the n h nu, okay, n h nu. So, for a particular frequency it can have this type of excited states, or higher energy states. Okay. So, here he assumed that since our crystal solid is made of n number of atoms, okay, and they are oscillating. So, they can take frequency so they are taking this similar frequency and mode is taking frequency. So, this it is oscillator also takes a frequency. So, for each mode having a particular frequency, okay, so it can have energy states, energy levels like harmonic oscillator. So, that he assumed, that he considered. Okay. Although initially he considered continuous medium, now he is considering this. There are atoms, atomic arrangement in the crystal. So, as if this mode are coming from the harmonic oscillation of the atoms, n number of atoms. Okay. So, that way he make it equivalent. Each mode is equivalent to a harmonic oscillator. So, harmonic oscillator have this n h nu kind of energy levels. So, each mode will have this kind of energy level. Okay. So, now you remember that now at a particular temperature this mode can stay in any energy level, in excited energy state. So, there is a probability to have here or here or here. So, there will be energy distribution, right. So, what was the energy distribution? Like that is Planck's formula. Okay. So, that for this particular mode it can stay in any of these energy states. Okay. So, but probability is different to have in different energy levels. Okay. So, that distribution is basically well known, that distribution, energy distribution among these different states, different energy levels. So, this is basically h nu by e to the power h nu by kBT minus 1, right. So, this is basically Planck formula, and that is the average energy of a harmonic oscillator that the energy distribution we got in Einstein theory also, right. So, here it is the basically one mode is equivalent to Einstein's one harmonic oscillator, right. There he considered all harmonic oscillators are oscillating with same frequency. So, that is why he multiplied with this the average energy of each oscillator. So, he multiplied with the 3n number of oscillators because having the same frequency, right. So, here this the average energy for each mode. In our case, this is the average energy of each mode means for each frequency, right. Now, our modes, different modes are not having same frequency. So, they have different frequency. So, this is the frequency density, that number density or density of modes are this. So, I have to multiply. So, for this frequency, what will be the energy? E equal to this Z nu into average energy is this, So, h nu by e to the power h nu by kBt minus 1. Okay. Okay. So, this is the average energy for frequency nu. Okay. So, this is the density. Okay. So, if I multiply it, so this will be the energy for a mode having the frequency nu. So, in that mode how many modes are there, in that frequency how many modes are there, this many modes are there, each are having this energy. So, I multiply it. Okay. Now, I have to integrate over the defined frequency. I have to integrate over the defined frequency d nu. Now, I have to integrate over the defined frequency. Now, 0 frequency starting from 0 to JL we take infinity. But in this case, now this Debye argued that that's frequency cannot be extended up to infinity. There will be cutoff of the frequency. Okay. So my total modes should not exceed number of 3n. Why 3n? This is the this number of total atoms in this or lattice point in this solid cube. We have taken cube there, number of these solids is this. So each mode, so I will get n number of mode. Okay, n number of atoms are there. So I will get number of modes also will be equal to that, like this. If I have n number of atoms in case of Einstein, you have seen. So n number of atoms. So I will get 3n number of modes because of the 3 degrees of freedom. Okay, in 3 dimension along the x, along the y, along the z. Okay. So here also I will get for 3 mode, but each mode have 3 degrees of freedom. So that is why this will be total mode, number of mode. Okay, means total frequency, number of frequency cannot exceed 3n, Okay. So I have to integrate this. So upper limit I have to take a particular frequency, so that this total, so that the total modes should not exceed 3n. Okay. So that I have to find out. So basically this is the density of states, density of modes. So density of mode is this, Okay. So now d nu. So if I integrate, I over the nu, I will get the total. So this is the number of modes. So I will get total number of modes. So this total number of modes has to be 3n. So for that, what will be the frequency limit? So that is called cutoff frequency, Debye frequency. So we write nu d. So we will find out the value of nu d. So here you can see 4 pi L square, this nu square. So I have to integrate over nu square d nu. So nu square d nu. Okay. So outside it will be 4 pi L cube. So L cube we can write V, volume of the cube. L cube we can write V, volume of the cube, right. And then divide by here one thing we have to do, this 4 pi V. So V is basically V is volume, it is L cube, So and then here this in case of string kind of things, or so here this we have 3 n number of modes, because this for 3 direction. Okay. So, if you consider the string, say string or this your 3 dimensional material. Okay. So, I think easy to understand considering string. So, if you take a string, so this vibration along this direction. Okay. So, this basically tell this longitudinal mode, and vibration along this direction or this direction, that is called transverse mode. Okay. So, velocity in case of transverse mode and in case of longitudinal mode are generally different, they are not equal. So, we have considered 3 n. So, since velocity are different, so I have to write separately. So, these 4 pi, so v cube. So, basically here I will write 2 mode transverse mode, 2 mode are there. So, 2 by V L, 2 by, no, I think I can take just I am. So, this is this. So, this is 1 by V cube. So, I am writing, so 2 by V square plus 1 by V square, right, 1 by V square. Since velocity are different for transverse and this longitudinal. So, 2 are transverse. So, here velocity I am writing V t, and here velocity I am writing V L longitudinal. So, since they are different, so we can replace 1 by V square by this. Okay. So, then fine. So, from here if you differentiate it, what you will get? You will get basically nu cube by 3, nu cube by 3 and nu d. So, you will get, if you integrate it, so you will get nu d cube by 3 by 3. Okay. So, integration done. So, I will get this 3 here, it will go, it will be 9 n, 9 n. So, so 9 n, and then nu d. So, what I am getting? I am getting nu d, I am getting basically nu d cube equal to 9 n by 4 pi v, 9 n 4 pi v, and then this I can write as, okay, just write 2 by v t square plus 1 by v l square. Okay. So, here also one should write this, when you are considering 3 n. So, one should write this. So, this is basically one can replace this by this one, right. So, here also one can write anyway. So, when we need, we will see. So, that is the, so one can find out the upper limit of the frequency, upper limit of the frequency, okay, nu d, and nu d is known to us. Okay. So, nu d is such that this we have considered the upper limit of the frequency such that it should not cross, this total number of modes should not cross, at least it has to be equal to the 3 n. Okay. So, it is now, so now this is the for new value, this is the energy, okay, for this many modes, right. Now, for d nu, so that will be the energy for now, if nu varies 0 to this. So, this is the energy for a mode of having frequency nu, and now how many modes are there with that frequency, that is this. Now, that will be the energy, this is the average energy for that mode having the frequency nu, okay, that will be the energy. Now, if I vary nu 0 to nu d, so that will be the total energy of the system. Okay. So, that I have to calculate, So, you replace E equal to, you replace this here I did again mistake, it is V cube. So, this is not V square, this will be V cube, this will be V cube. Okay. So, here you put this value, what is Z nu. So, this 4 pi V, L cube is V, divided by V cube is this 2 by V transverse cube plus 1 V L cube. Okay. So, then what I have here, I have, so then H also, so this I am putting here. So, if I put that one here, so this I am taking outside of this frequency, because it is the independent of frequency, H is independent of frequency, fine. Then frequency part I have to write inside, So, that is basically here I am getting here nu square is there. So, nu is here. So, it will be nu cube divided by nu cube, from here only nu square is coming. So, nu cube e to the power h nu by kBt minus 1 d nu. So, here I can write d nu. Okay. Okay. So, this, for integrating this one, I have to consider that. So, let us take x equal to h nu by kBt. So, dx equal to h by kBt d nu, right. So, when nu tends to 0, x tends to nu tends to 0, x tends to 0. When nu tends to nu d, x tends to h nu by kBt. So, from here, so for x nu tends to nu d, so I will get x d equal to h nu d by kBt. Okay. This x d here, if I define that h nu d by kb is theta d, d by temperature theta d, x d equal to theta d by T, where theta d is h nu d by kb. Okay. So, this now comfortable to us. So, here what I can do, here your nu cube. So, nu is kBt by Hx, So, this I can write 4 pi Vh by this term by this term, then here I can write 0 to x d, Now, nu I will replace by x. So, nu cube means I am getting kb by kbt by hx, So, kbt by h, okay, into x. So, x I will keep inside. So, nu cube. So, x cube. Okay. So, this will be cube, fine. Then divide by e to the power x minus 1, and for d nu I will get kbt by h dx, So, kbt by h, so it will be 4, okay, into dx. Now, here h is there, So, what I can do? So, 1 kbt by h I can take out. So, keep it 3, So, kbt by h, so h will go. So, here basically h is go. So, here kbt, okay. Now, you see this this part 4 pi v into this, if you take this side, equal to 9 n by nu d cube, right. So, 4 pi v by this term equal to 9 n by nu d cube. So, I can simply replace this. By 9 n by nu d cube, okay, Now, here it is cube, this is cube. So, this nu d cube I can put inside, okay, So, this is basically 9. So, n kb is, if it is for 1 gram mole. So, I can write R, 9R into T, and this I can write as I defined kb by what is this, h nu d by kb is theta d, h nu d by kb is theta d. So, this kb you take here kb. So, this is theta d. So, this I can write T by theta d cube, okay. So, then what I am getting, T by theta d cube, and then this part is so 0 to xd is nothing but theta d by t. So, this I can write theta d by t, this limit theta d by t, and then x is basically theta d by t, x is theta d by t. So, this I can write theta d by t, okay. This you keep it, So, this is x cube by e to the power x minus 1 dx. Now, you see this is the total energy of the system, So, now we have to integrate this one. Now, let us consider this first case, this at higher temperature, at higher temperature, at higher temperature. So, as I mentioned that there is no meaning of higher temperature, lower temperature without any reference. So, here at higher temperature means temperature is very greater than or greater than theta d, greater than theta d. Okay. So, then one can find out that theta d by t, theta d by t, that is nothing but x d, theta d by t, that is x t. Okay. So, theta d by t is very so t is very higher than theta d, right. So, this will be very less than 1, this will be very less than 1, this will be very less than 1, and this is nothing but this x, right, it is x. So, basically x is going towards the x is very small, x is very small, right. So, because x d ultimately here this x d will come, right, after integration. So, that is this term, this x, it is so this it is smaller term under this condition, it is very small to compared to 1. So, this you can e to the power x minus 1. So, it is equivalent to x, one can write this is x. So, this is x and this is x s cube, right. So, it will be x s square dx. So, x s square dx means x s cube by 3. So, x d cube by 3. So, this will give me this integration part will give me for lower temperature, it will give me x d by 3. Okay. So, x d, what is x d? Theta d by 3. So, x d is nothing but 1 by 3 theta d by t cube, right. Now, here you see t by theta d cube, here theta d by t cube. So, this will go and this 3 is there. So, it will be 3. So, I will get basically 3 r t. So, at low temperature total energy I will get E equal to, for low temperature I will get 3 r t. So, C v equal to del E by del t at constant V, right. So, it is equal to 3 r, So, at higher temperature it is correctly we are getting 3 r. Now, at lower temperature, so I think I will stop here and then I will continue in next class. Thank you for your attention.